27, I would start by distributing. We have x cubed times x squared minus x to the 5th plus 2x to the 8th. You should start by distributing that x cubed times x squared will give you x to the 5th. You're using this exponent rule right here to do that. Minus x to the 3rd times x to the 5th is going to be x to the 8th. Again, you're going to add those exponents. Then we have the plus 2x to the 8th at the end here. After that, you should look for like terms. Like terms means same variable, same exponent. I see that these two guys have the same variable and same exponent, so they can be combined. This is -1 copies of x to the 8th plus 2 copies of x to the 8th. That's +1 copy of x to the 8th. So that's our answer. 28. We have the expression 4x to the 5th, y to the 3rd, all squared. You should be thinking about where is it? Well, I don't see the appropriate exponent rule right here. I would argue that the rule that you should have in mind is the exponent rule, which says that ab to the c is equal to a to the c times b to the c. In other words, exponents distribute over products. What you have inside these parentheses is a bunch of stuff being multiplied. The 4 times the x to the 5th times the x to the 3rd, and all of those things are being squared, so you're going to distribute the square to each of those things. So 4 squared times x to the 5th squared times y to the 3rd squared. One thing that you should notice is the 4 gets squared as well. A lot of times students don't apply the exponent to the coefficient for some reason. 4 squared is 16. And now we have x to the 5th quantity squared, and for that you should be using this rule right here. Power of a power, you multiply the exponents, so that's x to the 10th, and then, I don't need these parentheses, and then y to the 3rd to the 2nd, same rule, you're going to multiply those exponents, you get 6. Okay, number 29, we have the expression 2x squared times 4x cubed plus 1 minus x to the 5th. Once again, I would start by distributing the 2x squared to the terms in parentheses, just like we did in 27. So 2x squared times 4x to the 3rd is, well, you multiply the coefficients. 2 times 4 is 8. As far as the variables are concerned, x squared times x to the 3rd, that's x to the 5th. You're going to add those exponents. Plus, and then 2x squared times 1 is just 2x squared, and then minus x to the 5th. And just like before, at this point, you should ask yourself, are there any like terms? Like terms means same variable, same exponent. And yep, sure enough, the first term and the last term have the same variable and same exponent, so they're like terms and can be combined. This is 8x to the 5th, take away 1 copy of x to the 5th, leaving you with 7 copies of x to the 5th, plus 2x squared. Number 30, we have the expression 3x cubed y times 2x minus y minus 6x to the 4th y. Again, I would start by distributing before you do anything else. So I'm going to distribute the 3x cubed y to the two terms in parentheses. I multiply these coefficients, so 3 times 2 is 6. As far as the variables, I have x to the 3rd times x. Plain old x is like x to the 1, so x to the 3rd times x to the 1. You add those exponents, that's this rule right here. 3 plus 1 is 4, so I get x to the 4th. And then just y minus 3x cubed y times y, that's just going to be 3x cubed y squared. And then this minus 6x to the 4th y is just chilling over there. And again, I ask myself, are there any like terms? Like terms means same variables, same exponent. I think the first and last term have the same variables and same exponents on those variables, so they are like terms. You can combine them. Well, it's just 6 copies of x to the 4th. Take away 6 copies of x to the 4th. Sorry, x to the 4th y. The first and third terms cancel, right? They totally cancel each other out. And you're just left with the negative 3x cubed y squared. By the way, notice the minus sign still here at the end. The minus sign here is attached to the term on the right. It's associated with the term on the right, not the one on the left. So even though this term has disappeared, the minus sign is attached to this term, so the minus sign is still there. Number 31, we have sort of like a power of a power of a power, x squared to the third to the fourth. You're just going to repeatedly use this rule here, like power of a power, which tells you that when you have one power raised to another, you multiply the exponents. So, you could do this one at a time. Like you could just sort of, look, it's x to the 2 times 3 times 4, which is 24. Okay, like you could think of it this way, like 2 times 3 is 6, and then 6 times 4 is 24. Or you could think of it this way, like 4 times 3 is 12, times 2 is 24. It doesn't make any difference. Number 32, we have the expression 4x cubed y to the 5th quantity squared times xy to the 6th. I would start by distributing this exponent and this exponent using, well, it's not an exponent rule which appears here, but I mentioned it earlier. It's the fact that if you have a times b raised to the c, that's a to the c, b to the c. In other words, exponents distribute over products. So what I obtain is 4 squared, and then x to the 3rd squared, and then y to the 5th squared, times, likewise distributing the 6 over here, x to the 6th, y to the 6th. So 4 squared is 16, and then x cubed squared, that's a power of a power. You're going to use this rule right here. That's multiplication, so x to the 6th. Y to the 5 times 2 is 10. And then we have the x to the 6th, y to the 6th over here. And finally, we're going to use this rule right here, power of a product. You're going to add the exponents. So 16, we have an x to the 6th here and another x to the 6th over here. That's going to give me x to the 12th. And then y to the 10th times y to the 6th, that's going to give me y to the 16th. Number 33, I have the expression x to the 7th over x to the 4th. You're just going to use this rule right here. We're going to subtract those exponents. So that's x to the 7 minus 4, which is x cubed. The end. Easy. Number 34, we have x to the 4th over x to the 7th. Same thing, we're going to subtract those exponents. Actually, there's 2 ways of thinking about this. I'll show you 2 ways to think about this. One is you can say, oh, that's x to the 4 minus 7, which is x to the negative 3. And then you could say to yourself, well, what does a negative exponent mean? If you scroll back up, a negative exponent basically means like a reciprocal, like a to the negative x is 1 over a to the positive x. So if I have x to the negative 3, that's 1 over x to the positive 3, and that's the answer. There's a different way of doing this problem, though, that I also like. X to the 4th, of course, is x multiplied against itself, like 4 times, and x to the 7th is x multiplied against itself 7 times. And what you'll notice is that a lot of these x's will cancel, right? Like, this first x here cancels this first x here, and then this second x here will cancel with that second x there. There's a lot of cancellation. And after all the cancellation, how many copies of x are you going to have left over? 3, right? So you're going to have 3 copies left over. And where are they going to be left over? They're going to be left over in the bottom because there were more copies of x in the bottom to begin with. There's nothing left on top. You don't write 0, you write 1. Okay. So I find that sometimes when you're manipulating expressions like this, instead of dealing with negative exponents, it can be a little easier to just say to yourself, like, okay, stuff is canceling. How many factors are going to be left over after that cancellation occurs? And where will those leftover factors be? Will they be left over in the numerator or denominator? So that's often how I think of these. Number 35, we have the expression 2x to the 5th over y to the 4th, all raised to the 3rd. I would start by using, I don't know if it's listed. I don't see the rule here. There's kind of, but there's a rule which says that if you have a over b to the c, then that's a to the c over b to the c. In other words, exponents distribute over the top and bottom of a fraction. So that's what I have here. So I'm going to distribute that 3 to the top and bottom of the fraction. So I have the entire numerator cubed and the entire denominator cubed. Now, in that numerator, I have several things being multiplied, 2 and x to the 5th, all cubed. You're going to cube both of those things. So it's 2 cubed, x to the 5th cubed. The denominator is kind of a simpler situation. You have a power of a power. In that situation, you multiply. That's y to the 12th. In the numerator, though, we have 2 to the 3rd is 8, and then x to the 5th to the 3rd, you multiply those exponents. That's x to the 15th over y to the 12th, and that's our answer. Number 36, we have the expression x to the 5th over y squared times y over x to the 4th. So whenever you multiply two fractions, you just multiply across the top and the bottom. So you multiply the two numerators and get x to the 5th y, and you multiply the two denominators, that's y squared x to the 4th. And then what I would do is I would think about cancellation. You could view this as a situation in which you should apply this rule right here, where you subtract exponents. Like, you could sort of say to yourself, oh, this is like x to the 5 minus 4, y to the, well, there's like y to the 1 here, right? Like a plain old copy of y is y to the 1. So I have y to the 1 minus 2. You can view it that way, but as I sort of explained in number 34, I kind of prefer instead to view these as problems in which a bunch of common factors are canceling in the top and the bottom of the fraction. So if I look at the x's, I have 5 copies of x on top and then 4 copies of x on the bottom. There's going to be a bunch of cancellation between those x's. After the cancellation is done, there will be just 1 copy of x left over, and it will be left over in the numerator because there were more copies of x in the numerator to begin with. Likewise, there's 1 copy of y here and 2 copies of y here. After cancellation, there will be 1 copy of y in the bottom. So that's how I tend to do these. 37, true or false? True or false questions are scary. True or false? That's false. So basically, yeah, I mean, so I will just tell you that this is not equal to 2x to the negative 3. The reason why is basically, so there's a couple ways of explaining it. One way of explaining it is PEMDAS. In other words, order of operations. All right, if you look at this x right here in the original expression, there are 2 operations being applied to it. It's being multiplied by 2. That's 1 operation, and it's being raised to this exponent, negative 3. PEMDAS, the default order of operations, says exponents occur before multiplication. So if I'm looking at this expression, I understand that the convention, the default order of operations, which PEMDAS tells me to carry out, is first I should raise x to the negative 3, and then after that I should multiply by 2, right? So that's the order of operations in this expression. Over here, the parentheses are changing the ordinary order of operations. They're changing the default order of the operations which PEMDAS imposes. The parentheses here are saying, actually, I want to multiply by 2 first, right? Which is not what happens over here. So the parentheses are saying, I want to multiply by 2 first, and then raise the result to negative 3, as opposed to raising to negative 3 first and then multiplying the result by 2. So they are different. That's one way of explaining it. A different way of explaining it, and this is probably a lot shorter, is that By default, by default, that is, unless you have something modified by parentheses, by default, exponents only apply to the thing directly in front of them. Okay? This -3 only applies to the object directly in front of it. In other words, the x. It does not apply to the 2. Okay? However, over here, the parentheses are forcing the -3 to apply to both things, both the 2 and the x. So another way of thinking about the difference between these two expressions is basically here you have the default behavior of an exponent only applying to the thing directly in front of it. That's the x. But here we're grouping the 2 and the x together as a single object. So now the -3 is applied to both of them. The right-hand side, so just to be clear, the left-hand side can be thought of as 2 times x to the -3. Like you can kind of view them as being separate objects. X to the -3, according to the negative exponent rule, that's 1 over x cubed. And so, and if you multiply these two guys together, you can think of the 2 as a 2 over 1. That gives you 2 over x cubed. So that's what the left-hand side is. The right-hand side is something quite different. Applying the negative exponent rule to this says take 1 over the object, the entire object, which is being raised that negative power, and change the exponent to be positive. Now, distributing that 3 to both the 2 and the x, because exponents distribute over products, that'll give you 2 cubed, which is 8, x cubed. So you can see the left-hand side is 2 over x cubed. The right-hand side is 1 over 8x cubed. Those are obviously very different. So probably more explanation than you needed, but I think that's a very important problem. There's a lot going on conceptually. 38, we have the expression 4 minus 4x over 6x minus 6. This is a little different from the previous problems. You need to pull out, it's not really exponent rules. It's more like factoring and canceling common factors, which is kind of not really the vibe of this section, but whatever. So in the numerator, I'm going to pull out a common factor of 4, which leaves me with 1 minus x. And in the denominator, I'm going to pull out a common factor of 6, which leaves me with x minus 1. How do you simplify an expression like this? Well, the 4 over 6 can be reduced. Like, think about reducing the fraction 4/6, like 4 over 6. That reduces to 2/3, right? You can do that here, even though there's like other stuff, you know, the 1 minus x and the x minus 1, that doesn't prevent you from reducing the 4 over 6, as you ordinarily would if it were by itself. The bigger mystery is like, what's up with the 1 minus x and the x minus 1? Do those cancel? Because, you know, like they're almost the same factor. If they are, in fact, the same factor, then like, yeah, they cancel. Are they the same factor? The answer is no, not exactly. Because look, if you compare like, because if you change the order of subtraction, you get something different. 7 minus 10 is -3. But on the other hand, 10 minus 7 is +3. So changing the order of subtraction, it does give you a different result. However, it does give you, like, the difference is kind of predictable. If you change the order of the subtraction, what that does is it changes the sign, right? So 7 minus 10 is the opposite of 10 minus 7. And we can actually use that fact here. What I'm going to do is I'm going to rewrite 1 minus x. I'm going to change the order of subtraction. I'm going to change that to x minus 1. But doing so produces the opposite of what I had originally, right? Changing the order of subtraction produces the opposite of what I had originally. You know, technically it's like 2 times negative x minus 1, but you can just put the minus sign over here in front. So now I literally have the same fraction top and bottom, and so I can cancel those common factors and get -2 over 3. Number 39. Again, this is like not really like an exponent rule problem. This is kind of more like factoring and canceling common factors. But whatever. So what you're supposed to do here is factor the top and bottom and then look for common factors, and if there are any, then cancel them. The denominator is pretty easy to factor. You're because the lead coefficient is a 1, so you're just looking for a pair of numbers that multiply to 6 and add up to -5. That's -2 and -3, so that's how that guy factors. The numerator is kind of a more annoying to factor. If you want to factor that using a box method or whatever method you like, that's fine. The method that I strongly prefer for factoring quadratics like this, where the lead coefficient isn't 1, is splitting the middle. So I look at 3 times -15, which is -45. So let me just jot this down, -45. And I look at the middle coefficient, which is -4. I'm looking for a pair of numbers which multiply to -45 and which add to -4. Okay, so that's what I'm looking for. I think -9 and 5 do the job. -9 times 5 is -45. -9 plus 5 is -4. So -9 and 5 are the two numbers I'm looking for. And what I do is I use those two numbers to rewrite the middle term. -4x, I'm going to rewrite that as -9x plus 5x. What you'll notice is like, this is like that right there, that's -4x, right? So I haven't actually changed anything, right? Now, why in the world would you do that? Why would you rewrite the middle term in that fashion? Well, because now what you should do is look at the first two terms here. They should have a common factor, okay? Pull the greatest common factor out of those first two terms, which is 3x. So I'm going to pull 3x out of just the first two terms. Pulling 3x out of 3x squared leaves me with x. Pulling 3x out of -9x leaves me with -3. Cool. Plus, now I'm going to do the same thing to the second two terms. I'm going to pull the GCF out of those second two terms, which is just 5. So I'm going to pull 5 out of 5x, that leaves me with x. Pull 5 out of -15, that leaves me with -3. Well, now wait a minute. I've got an x minus 3 here and an x minus 3 here, which means that in the numerator, x minus 3 is a common factor, which I can then pull out from these two terms, right? Like, in other words, so this whole thing there, that's one term. This whole thing here, that's a second term, and x minus 3 is a common factor appearing in both terms. When I pull x minus 3 out of the first term, I'm left with 3x. And when I pull x minus 3 out of the second term, that's 5. You might look at that and be like, oh my god, why would you ever do it that way? I prefer the box method. Yeah, but the thing is, if this is the first time you've ever seen this method, right? The first time you see it, it sounds complicated, but if you practice it, it's really fast, and there's no guessing. There's no guesswork, okay? Like, you don't have to guess and check, which is what the box method kind of is. You're just guessing numbers and hoping it works out. There's no guessing with this, okay? I don't like guessing problems. I like just solving them. Anyway, that's a little bit of trash talk about the box method, but that's okay. X minus 3 over x minus 3, they cancel, and you're left with 3x plus 5 over x minus 2. So, voila. Number 40. Again, this is like not really exponent rules. It's really more factoring and canceling common factors. The numerator is so it's x squared minus y squared over quantity y minus x squared. The numerator is a difference of two squares, like it's one thing squared minus another thing squared. In general, that factors as like a product of a sum and a difference. This is something you should sort of just memorize. X squared minus y squared factors as x minus y times x plus y. The denominator, it's y minus x squared. If you like, you can think of that as, this is sort of a tricky problem. You can think of that as y minus x times y minus x. And you might say to yourself, can I cancel anything here? Because, you know, like, in the numerator I have an x minus y, and then in the denominator I have a y minus x. And, you know, maybe I can cancel those things. But no, you can't. This is kind of the discussion that I had in number 38. So if you want more details on this, go to number 38. But basically, I can cancel this. I can change the order of subtraction in one of the factors. Like I can change this to x minus y as long as I throw a minus sign on the outside. Okay, so you can change the order of subtraction as long as you put a minus sign out there. So now I have an x minus y here and an x minus y here. Those guys cancel, and I'm left with x plus y over negative quantity y minus x. You might as well just distribute that minus sign and get yourself x plus y over... When you distribute the minus sign, you get negative y plus x, which of course is the same thing as x minus y. There's a different way of thinking about this problem, which is that... So again, the numerator factors in this way. You could alternatively say to yourself, okay, y minus x quantity squared, I'm going to change the order of subtraction, but that produces a minus sign. Okay, like I can change y minus x to x minus y, but that produces this minus sign. And you might say, oh, like that changes the value of the expression. But wait a minute, this whole thing is being squared, right? When you square a negative, the negative goes away. Like negative 3 quantity squared is just 9. So actually you can like ignore the minus sign here because it's being squared anyway, and you just have x minus y quantity squared. And then this copy of x minus y cancels with one of the copies of x minus y in the bottom. And so you're left with just one copy of x minus y in the bottom, which is what we had here. So hopefully... I don't know, you could think of that in either way. Hopefully you like at least one of those explanations. Oh, I skipped a problem, didn't I? That was number 41. Sorry about that. Okay, that was number 41. Let's go back to number 40. Number 40, sorry about that. Number 40, the actual number 40 is 3x over y cubed all raised to the negative 2. So there's a few ways to think about this. Here's kind of a painful way to think about this. You could say to yourself, oh, like, I'm going to distribute the negative. So first of all, like, there's kind of a rule which says that if you have a fraction a over b raised to a common exponent, then that exponent distributes, okay, to the top and the bottom. And so we could use that to say, oh, like, this negative 2 is going to distribute to the entire numerator and the entire denominator. You could say that. And then you could say to yourself, oh, well, like, this negative 2 distributes to the 3 and the x separately. And so I get 3 to the negative 2 and x to the negative 2. And then here I have a power of a power, so I multiply them and I get y to the negative 6. And then you can remember, hopefully, maybe, sort of, how negative exponents work inside of a fraction. Basically, negative exponents inside of a fraction, they sort of trade places. So this 3, because it's being raised to a negative 2, to a negative number, the 3 actually goes downstairs, and the negative 2 becomes positive. Likewise, this x to the negative 2, because it's a negative exponent, it goes downstairs, and the 2 becomes positive. Finally, the y, it's being raised to a negative exponent, so it goes upstairs and becomes positive. That's kind of the effect of negative exponents inside of a fraction, is they make the object to which the exponent is being applied switch between numerator and denominator. And when you make that switch happen, you change the exponent to be positive, okay? And then you can say, okay, fine, that's y to the 6th over 3 squared is 9, so 9x squared. That's kind of painful, though. Look, let me show you something a lot better. In general, and this is sometimes not really spelled out as an exponent rule, because it's not really, it's kind of just a consequence of the other rules that you've already seen. But if you have a fraction raised to a negative power, that's actually the same thing as flipping the fraction upside down and changing the exponent to positive. That's actually really useful to know. Okay, that's really useful to know. The proof of that is pretty simple. It's because, look, if you distribute the negative c to the top and bottom of the fraction, and then you say to yourself, you know, what I was saying a moment ago, oh, negative exponents, this guy is going to go downstairs, and the exponent's going to become positive, and then this guy is going to go upstairs, and it's going to become positive. And then you can say, oh, b to the c over a to the c, that's b over a to the c. So that's the proof of that. But I think that like, even though it's not often spelled out as a separate rule, it's really worth knowing. Like, so if you have a negative exponent applied to a fraction, just flip the whole fraction upside down and make the exponent positive. It'll make your life a lot easier. So this guy here, I'm going to apply that logic, like that rule here. So 3x over y cubed to the negative 2, I'm just going to flip this thing upside down and make it positive. Okay, now I no longer have to think about negative exponents in this problem at all. And all of this stupid crap is just, I can just ignore all that stuff. So now I'll just distribute, right? So I'm squaring both the numerator and the denominator because exponents distribute to the top and the bottom of fractions. That's y to the 6th over 9x squared. Okay, much faster. I prefer that method. Yeah, okay, cool. So we did 41 earlier. Number 42, I have x cubed plus 4x squared minus 21x over x cubed minus 9x. Again, this looks like factoring and canceling common factors. In the numerator, I see a common factor of x, which I can pull out from all three terms, which leaves me with x times x squared plus 4x minus 21. In the bottom, there's also a common factor of x, leaving me with x squared minus 9. In the numerator, x squared plus 4x minus 21, because that quadratic starts with a lead coefficient of 1 here, I'm just looking for a pair of numbers that multiply to negative 21 and add up to 4. So I think that's 7 and negative 3. So x plus 7 times x minus 3, that's how that guy factors. X squared minus 9, that is a difference of two squares. That factors as a sum, as a product of a sum and a difference, right? Like if you have a squared minus b squared, that's a plus b times a minus b. That's just a fact that you should sort of memorize or know. So that x squared minus 9 factors as x plus 3 times x minus 3. And then we can see that there's a lot of cancellation. These two x's cancel, and then these x minus 3's cancel, and you're left with just x plus 7 over x plus 3. Number 43. Okay, so we have this grotesque looking expression, x to the negative 4 to the 5th times x squared over 5x to the negative 4. The first thing I would do is I would apply the power of a power rule to this guy. It's x to the negative 4 to the 5, so we multiply those exponents. We get x to the negative 20, x squared, 5x to the negative 4. Then I would say these two guys, you're going to add those exponents. So that's x to the negative 20 plus 2 is negative 18 over 5x to the negative 4. Then I would sort of say, oh, you've got negative exponents inside of fractions. What that means is, as I sort of addressed earlier in like problem, I don't know, I don't even remember what it was, but when you have negative exponents inside of fractions, they sort of trade places, like from numerator to denominator, and the exponents become positive. So this guy here, the x to the negative 4, that goes upstairs, and the exponent becomes positive. And this guy here goes downstairs, and the exponent becomes positive. Notice the 5 does not go anywhere. It's not, because the 5 is not affected by this exponent. By default, I was saying this earlier, by default, exponents only affect the thing directly in front of them. So the negative 4 is being applied to the x, but not to the 5. So the 5 doesn't move, doesn't go into the numerator or anything. And then I would just say, like you got a bunch of copies of x on top and bottom. There's going to be a bunch of cancellation. 4 copies are going to cancel. You're going to be left with 14 copies. Where are those leftover copies going to be? They're going to be in the bottom. So you're going to have 5x to the 14th at the bottom. What's left in the numerator? Oh, there is something. It's 1. Okay, like whenever everything cancels, you've got a 1. You could alternatively think of this as like x to the 4th minus 18, which is x to the negative 14, but I think it's just easier to view it as cancellation. Number 44, we've got x squared minus 4 over 5ax plus 10a. Again, I'm looking to factor this stuff. Numerator is a difference of two squares. That's x plus 2 times x minus 2. The denominator, there's a common factor of 5a, which when I remove that, I'm left with x plus 2. And this x plus 2 and that x plus 2 will cancel, leaving me with x minus 2 over 5a. Sweet. Number 45, we have y to the 5th, x to the negative 3 over y to the negative 7, x to the 11th. I would say, again, negative exponents mean that the object switches between top and bottom of the fraction. So the y to the 5th is staying where it is because it has a positive exponent. The x to the 11th is staying where it is because it has a positive exponent. But the x to the negative 3, that guy is going to go downstairs because it has a negative exponent, and the exponent is going to become positive. This y to the negative 7th, that guy is going to go upstairs, and the exponent is going to become positive. Then I can do a little bit of simplification. Y to the 5th times y to the 7th, you're going to add those exponents. That's y to the 12th. And in the denominator, that's 11 plus 3 is 14. I think that's it. Number 46, we have 4x squared y cubed over 24x cubed y cubed minus 36x cubed y to the 4th. So again, I'm looking for common factors and stuff. There's nothing to do in the numerator because there's only one term to begin with, but I think that there's a common factor I can remove in the denominator. Looking at the coefficients, I can definitely pull out a 12. Looking at the variables, I can definitely pull out some number of copies of x. I think I can pull out x cubed from both terms. So x cubed, and I can pull out some y's as well, but the most I can pull out from both terms is y cubed, right? Because this one only has y cubed to give. Now, what's left over in these two terms after I remove that common factor of 12x cubed y cubed? Well, from here, when I factor 12 out of 24, I'm left with 2. There are no more x's left over, and there are also no more y's left over, so I think I just have 2. And then minus what's left in this term? Well, I factored 12 out of 36. That leaves me with 3. There were 3 copies of x. I removed 3 copies of x, so there are no copies of x. However, there were 4 copies of y originally, and I removed 3 copies, so there's still a copy of y right there. Okay, and then I can see, first of all, the 4 and the 12, that's like a fraction. You can reduce it just like you ordinarily would. 4 over 12, that's 1 over 3. And then I've got an x squared here and an x cubed down below. You're going to have some cancellation. There's going to be 1 copy of x left over, and it's going to be in the bottom. You've got y cubed here and y cubed here, so actually the y cubes just cancel each other out entirely, and I still have that 2 minus 3y in the bottom. That's 46. Number 47, I have 5xy cubed quantity to the negative 2, x cubed y to the 4th. I would start by distributing. Again, it's sort of the rule that a times b to the c is a to the c, b to the c, like exponents distribute over products. So that's what I'm going to do in that first set of parentheses. I've got 5 to the negative 2 times x to the negative 2, and then y is already being cubed, and I'm raising that whole thing to the negative 2. Then I have the x to the 3rd and the y to the 4th. Now, because of the negative exponents, I am going to have a fraction here. Let me just do one thing really quickly. I'm just going to take care of this guy right here. Y to the 3rd to the negative 2. You multiply those exponents, that's negative 6. X cubed y to the 4th. Now, negative exponents, as I sort of said before, negative exponents cause things to switch between the numerator and denominator. Right now, there isn't a denominator present at all, but the fact that there are negative exponents is going to create a denominator, and a bunch of stuff is going to go into that denominator. The 5 is going to go into the denominator, and the exponent becomes positive. This guy is going to go into the denominator, and its exponent will become positive. This guy is going to go into the denominator, and its exponent will become positive. However, these two guys have positive exponents, so they stay exactly where they are. Now I think about cancellation. I know that these x's here, there's going to be some cancellation between the x's, and the leftover copy of x is going to be, there's going to be 1 copy of x left over, and it will be left over in the numerator. The y's, there's going to be 2 copies of y left over, and it's going to be in the bottom. And then finally, there's also that 5 chilling at the bottom. So that's my answer. Number 48, I have 3x to the negative 2, y to the negative 1, z to the 4th, over 5x to the negative 4, y squared, z to the negative 7. Again, it's just about moving around the stuff with negative exponents. I want to emphasize once again the 3 and the 5 are not affected by these exponents at all. Exponents only affect the thing directly in front of them, so the 3 and the 5 are staying exactly where they are. However, this x to the negative 2, that guy is going to go downstairs, exponent becomes positive. This guy is going to go upstairs, exponent becomes positive. This y to the negative 1, that goes downstairs and becomes positive. This y squared stays exactly where it is because it has a positive exponent. It's not going anywhere. This z to the negative 7 is going to go upstairs, and the exponent becomes positive, and this z to the 4th stays exactly where it is because it's got a positive exponent. There's a little bit of combination I can do here, like z to the 7th, z to the 4th, you add those exponents, that's z to the 11th. And then y to the 1, y squared, that's y cubed, adding the exponents. And then I can just, the only other thing I can do is I can cancel those x's. There's 4 copies of x on top and 2 on the bottom, so there's going to be 2 copies left over after cancellation. And of course, they're going to be in the numerator. I think that's my answer. I'm doing these pretty fast. I hope I'm not screwing up. I've probably screwed up a couple times. Let's keep it real. All right, number 49, last problem for today. 3x to the negative 4, y over 4x cubed, y to the negative 6. Yeah, once again, the stuff with negative exponents is going to move around. And yet again, I'm going to emphasize this 3 here is not affected by that exponent of negative 4. Likewise, this 4 is not affected by that 3. So the 3 and the 4 stay where they are. But this x to the negative 4, that guy's going to go downstairs, and the exponent becomes positive. This y to the negative 6, that guy's going to go upstairs, and the exponent becomes positive. I also had a plain old y in the numerator, which is still there, and I also had a plain old x cubed in the denominator, and that's going to stay there. So that's 3y to the 7th, right? Because this y is like a y to the 1, you add the exponents, and then 4x to the, again, you're adding the exponents here, x to the 4th, x to the 3rd is x to the 7th. So I think that's it.